We can never touch a star. We can never visit one or scoop up a sample or bring a single piece home. Our own sun would vaporize any spacecraft long before it ever arrived. And every other star is so far away its light takes years, sometimes thousands of years, to reach us. And yet, we can tell you exactly what a star is made of. Not a vague guess, but a precise recipe, element by element, for a fire we will never reach. So how on earth do we know what the stars are made of? The answer hides inside the only thing a star ever sends us: its light. Learn to read that light, and every star in the sky becomes an open book. This is the story of how we learn to read the stars. It begins with something you have seen 100 times, a simple rainbow. Sunlight looks white or maybe pale yellow, but white light is a kind of lie. In 1666, a young Isaac Newton let a beam of sunlight pass through a glass prism. The prism bent the light, and out the other side spilled every color of the rainbow. Red, orange, yellow, green, blue, and violet all fanned out into a band he called a spectrum. White light is really all of these colors layered together, pretending to be one. Bend the colors back together, and they turn white again. Newton had taken light apart. But for over a century, nobody looked closely enough at that band of color, until one obsessive craftsman built a prism sharper than any the world had seen. In the early 1800s, a German named Joseph von Fraunhofer made the finest glass on Earth. He ground lenses so pure and precise they ended up in the world's best telescopes. To test his glass, he spread a beam of sunlight wider than anyone before him. He expected a smooth, unbroken ribbon of color. That is not what he found. Scattered across the rainbow were dark lines, thin, sharp gaps where the color simply vanished. Picture the perfect spectrum, every color flowing seamlessly into the next. Now look closer, hundreds of narrow black lines as if colors had been plucked out. Fraunhofer counted more than 500 of them and carefully mapped their exact positions. He never knew what they meant, but he knew they were real and always in place. These missing colors became known as Fraunhofer lines, and they were a hidden code. But what could possibly reach down from the sun and steal exact colors from its light? The answer came from a laboratory bench and a very hot, very clean flame. In 1859, two Germans joined forces, a chemist, Robert Bunsen, and a physicist, Gustav Kirchhoff. Bunsen had built a burner with a nearly colorless flame. You know it as the Bunsen burner. When they dropped different chemicals into that flame, its color changed every time. Table salt burned a vivid orange yellow, copper glowed green, lithium flared a deep red. Every element, they realized, burned with its own signature color. But the true magic appeared when they sent that flame's light through a prism. Each element gave no full rainbow, only a few bright, sharp, isolated lines. Sodium glowed at two precise spots of yellow, always those two, nowhere else. Hydrogen had its own pattern, helium another, iron a dense thicket of many lines. This is a fingerprint, not for a person but for a chemical element. No two elements share the same set of lines. Each pattern is completely unique. And then Kirchhoff noticed something that stopped him cold. The bright lines of sodium sat at the exact spots as two dark lines in the sun. The colors sodium gives off are the very colors the sun's light was missing. It was no coincidence at all. It was a message. Here is the rule Kirchhoff uncovered. A hot, glowing gas emits its own bright colors. But a cooler gas, in front of a bright source, absorbs those very same colors. Heat sodium on its own, and it emits two bright yellow lines. Now shine white light through cool sodium, and those same two lines turn black. The element leaves its fingerprint either way, bright lines or dark ones at the same address. So the dark lines in sunlight are not empty, they are a list of ingredients. Each missing color names an element floating in the sun's cooler outer layers. The sun was telling us its own recipe. We only had to learn the code. And with that, humanity could weigh the heavens without ever leaving the ground. Starlight through a prism reveals dark lines, and each dark line names an element. And almost at once, the starlight delivered a shock nobody was prepared for. On the 18th of August, 1868, a total solar eclipse swept across India. Astronomers aimed their instruments at the sun's glowing edge and split the light apart. There in the spectrum sat a bright yellow line, close to sodium but not quite matching. It matched no known element anywhere on Earth, not a single one. A French astronomer, Jules Janssen, recorded it. An Englishman, Norman Lockyer, studied it too. Lockyer made a bold claim. This line belonged to a new element found only in the sun. He named it after the Greek word for the sun itself, helios, helium. An element discovered inside a star before anyone had ever found it on Earth. For nearly 30 years, helium stayed a purely solar element, a ghost living in sunlight. Then in 1895, it was finally found on Earth, seeping from uranium ore. The same yellow line, the same fingerprint, the light had been right all along. If light could reveal a whole new element, what else was it quietly telling us? For decades, everyone assumed the stars were made of much the same stuff as Earth. Rock and metal and familiar elements, only far, far hotter. It seemed obvious. Then, in 1925, a young woman at Harvard looked deeper than anyone before. Her name was Cecilia Payne, and she was writing her doctoral thesis on starlight. She measured the strength of the spectral lines and did the hard physics behind them. The math told her something so strange, she almost refused to believe it herself. The stars were nothing like Earth. They were overwhelmingly hydrogen, the lightest element of all. By mass, a star like our sun is roughly 74% hydrogen. About 24% is helium, and everything else combined is barely 2%. Iron, oxygen, carbon, gold, every other element together, just a thin sliver. Stars are essentially two gases, the two simplest, lightest gases in the whole universe. It was one of the most important discoveries in the entire history of astronomy. And at first, the senior scientists insisted she simply had to be wrong. A famous astronomer pressed her to call her own results spurious. Cautiously, she did. But within a few years, new measurements proved her completely, undeniably right. Cecilia Payne had read the recipe of the stars. The universe was mostly hydrogen. By now, light had told us what stars are made of, but it held one last secret. Because those fingerprint lines can do more than name elements, they can also move. Think of a siren, its pitch rising as it races toward you, then dropping as it leaves. Light behaves in a strangely similar way. Motion itself shifts its colors. If a star races toward us, its lines slide toward the blue end of the spectrum. Here is an element's pattern, measured at rest in a laboratory here on Earth. And here it is in a distant galaxy. The whole pattern shifted toward the red. That shift toward red means the object is racing away from us through space. The pattern is unmistakable. The same fingerprint, the same spacing, simply moved along. In 1929, Edwin Hubble noticed almost every galaxy was shifted toward red. The farther a galaxy sat, the faster it fled. The whole universe was expanding. That staggering idea came from reading shifted lines in faint, distant starlight. The same dark lines that name a star's ingredients also clock its speed and distance. One thin bar of missing color, carrying the ingredients, the motion, and the history of a star. So let us return to that impossible question we began with. We can never touch a star. We almost certainly never will. But we do not need to, because every element writes its signature straight into light. A barcode of missing colors, unique, unmistakable, and utterly, completely honest. Split a beam of starlight, and you are reading a message the star could not help but send. Light that may have left its source thousands of years ago, before cities, before writing. The number of stars humanity has ever physically touched, exactly 0. And still we know their ingredients, their temperature, their motion, and their age. We even found a brand new element in the sun, before we ever found it here. All of it read from a whisper of light, split into a rainbow, decoded line by line. The stars have broadcast their composition since long before we ever learned to listen. We simply learned the alphabet, an alphabet written entirely in missing colors. So the next time you look up at a still, silent night sky, remember this. Every one of those tiny points of light is telling you exactly what it is made of. You are not merely seeing the stars anymore, you are reading them. A fire we can never reach, whose recipe we already know by heart.